Hello. So am I audible?
Yes, sir.
Okay. So we'll just start in a minute. So hello. Good evening, all. So my name is Parth Joshi, and so I'll be conducting these online sessions every week for this course. So I am basically a PhD student in the Department of Mechanical Engineering at IIT Bombay, and as a part of the Prime Minister's Research Fellowship, so I am getting an opportunity to interact with all of you. So thanks for joining this session. So, so we'll be basically discussing about the course content for that particular week, and so we'll be discussing about your, uh, whatever problems that you may have related to the assignments or to the related to the course content, or so I'll be basically try to answer those. Uh, so broadly, I am basically working in the area of electric and hybrid electric vehicles. I'm mainly focusing on the energy management part, and I've also worked in industry for a few years. So that's about my brief background. So welcome all to this session. Yeah, so I think someone else also has joined. So I think Mr. Prashant. So I think have you joined for the first time, or have you joined before as well? Okay, so you missed the session one. Okay, second. Okay, fine. So if you have any questions related to the second week's course content or this week's course content, so you can like ask them, so we can discuss them. Uh, yeah, okay, fine. Okay, so if like, yeah, so Mr. Amit Bansal has raised his hand, so yeah, can you,
Yes, sir.
yeah,
Yes, sir. Good evening, sir.
yeah, good evening.
Sir, as we have discussed in the last live session, sir,
Yeah.
the query raised on the discussion forum is yet to be replied, sir. It has been already 1 week or more, sir.
Okay, okay. So I'll just check that. So I was not really able to get time to go through that. So but yeah, so I'll definitely go through that. Yeah. So what was the question? So if you can just tell me, like,
Sir, the same question, sir, which we have discussed in the live session also.
mm-hmm.
None of the answer is correct in the given option.
Okay,
But since the last date has already gone and the evaluation has done already,
okay.
but that data has not been included, sir. That means the wrong answer has been evaluated as the correct one, sir.
Oh, okay. Oh, okay. So I think then in that case, yeah. So then, uh, so just a moment. I am just opening the course page, so we can just discuss that immediately if you want. Yeah, so I'm sharing my screen. Like I have opened the discussion forum page. So can you see
Yes,
that?
yes, sir. I can see, sir. The question number 5 of assignment 2, sir. We have already solved this question in the live session on Tuesday, sir.
Okay. So I have opened like the spring constant of a cantilever being
Sir,
having
yeah,
lambda.
sir. This has been already been replied by the NOC NOC team, sir. So my
Okay.
concern is regarding assignment number 2, question number 5, sir.
This one, like the one which I opened, this one. Did you mean this one?
No, no, sir. Sir, my concern is regarding question number 5 of assignment number 2, sir.
Okay.
Sir, Mr. Prashant has raised the issue on the discussion forum, sir. You can check his message, sir.
Okay.
Yes, sir. This one, sir.
Oh, okay. 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 So I think, yeah. So then maybe I'll try to email the professor and yeah, I think so. I'll just email regarding this concern and let you know. So because since you mentioned that you like
Okay, sir.
already have gone through the solution, right? So I think we'll not go through the solution of this again, right?
Yes, sir. We have already discussed in detail. The same question you have discussed in the last live session, sir.
Okay, okay,
And we have verified the answer. The answer is not available in the given option, sir.
okay, okay. Fine. So I think then maybe, yeah, I think I can email uh, the professor and yeah, let you know. I think you can also try to do the same. Like I think you can also just try to contact the professor concerned and
Sir, actually, I have tried to contact the NPTEL at IIT Mumbai, IIT Madras, sir.
yeah,
Sir, they have advised me to they have advised right on the discussion forum only, sir.
okay,
Because generally the course coordinator doesn't handle these types of query. Either TA or any other person assigned from
okay,
a particular institute, sir. Th-
okay, okay,
He is the authorized person to re-evaluate these types of queries, sir.
okay. So fine. So maybe I'll reply to this post and yeah. So I'll also maybe check with the professor or NPTEL team whatever like and let you know.
Okay, fine, sir.
Okay. Any other concerns?
So no from my side, sir.
So this question which I have opened is regarding assignment 3. So yeah, so I think I will not be able to answer it right now. Maximum value of the magnification factor. Okay. Okay, so this actually I can just give you a hint that just go to the definition of the magnification factor like and then try to put in this particular case in that. So yeah, fine. So I think okay, so you already got an email regarding this.
Yes, sir. Actually, we are getting a reply to our individual email ID. The replies are not made on the discussion forum by the concerned person, sir. So
Okay,
I am not concerned about what he is replying to other people, sir. So I think it is better the reply can be put on the discussion forum only, sir. So other
Yeah,
can also know the answer, sir.
yeah, exactly. So others may also have the same question. Yeah.
Yes, sir.
So
Yes,
that
sir.
we reply to all the person actually. So that it's available to everyone. Yeah.
Yes, sir. Yes.
Yeah. Anyway, uh, any other like questions that you had like related to the course content for this week or previous week? No. Okay. 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 Fine. So then, so I had prepared a few slides regarding the brief overview of the content which was covered in this week. So do you think we should go through that or we can skip that?
Sir, my request is that first we will go through the content, sir, because I have some doubts in this week, sir.
Oh, okay, sure. Yeah, just a moment. So yeah, so this is about the brief overview of the course content related to this week. So the topics that have been covered are basically harmonically excited vibrations. So where you have uh, a, a periodic force that is being basically applied on a system. So which has basically the variation of that force is generally sinusoidal or harmonic. So so basically we have discussed about the response of the system to such a harmonic excitation, and then the definitions of the magnification factor and the frequency response curve has been basically covered. So magnification factor meaning basically the steady state response, uh, and the basically we consider some quantity which is corresponding to, let us say, the static deflection corresponding to the excitation, and the steady state response to the harmonic excitation. So basically a ratio of that we can call it as a magnification factor. And the frequency response is basically uh, which measures, basically it shows the uh, so it has two parts. So the frequency response has basically amplitude and phase. So one part is the amplitude as a function of the frequency. So amplitude meaning basically the amplitude of the steady state response, and the value of the phase uh, as a function of the frequency. So as we go on increasing the frequency of the harmonic excitation, how does the steady state amplitude value of the response change, uh, and how does the phase angle change basically with respect to the frequency. So that's a very important part, so which needs to be understood. Then there is some discussion about the rotating unbalance, so which again is essentially becomes a harmonically excited vibration. So sometimes there is a imbalance in present in some machines, which causes a rotating unbalance. So that can be modeled as a harmonically excited harmonic excitation. And similarly, like excitation of the support can also be thought of, like where suppose if a machine is mounted on a foundation, and if the foundation itself is subjected to some vibration, so how much of that vibration is being transferred to the system, so that part is becomes important in that case. And yeah, and the energy input and the dissipation by viscous damping, so that is also another topic that has been covered in this uh, week. So yeah, so first, the case of like the forced vibration for an undamped system has been discussed. So, so here we basically have the differential equation, which is the second one, which is shown over here. So this is for an undamped system, and this is like if we have a damping present. So x by delta static here is basically, so the capital X here is the steady state response of the system, and delta static is the static deflection corresponding to a constant force with magnitude F naught. So, and for a spring with stiffness K, so delta static will be basically F naught by K. So this ratio becomes 1 upon 1 minus the ratio of omega by omega n squared. So, so the plot of this function, basically x by delta static with respect to the ratio of the frequency, so ratio with respect to the natural frequency omega n. So that is plotted over here. So it looks like a hyperbola, like a figure. So here at when r is equal to 1, which means basically at resonance, the ratio of x by delta static goes to infinity or minus infinity, depending on which part of the curve we are looking at. So this is for forced vibrations for an undamped system. So here, because there is no damping present, the amplitude actually goes to infinity. So mathematically, so it corresponds to like infinite amount of energy being added into the system. But in reality, we always have we always have some kind of damping present in the system. So so therefore the frequency response curve, they look like these, like, so the figure on the left hand side is basically the variation of the amplitude ratio with respect to the frequency ratio, and the and this figure on the right hand side shows the variation of the phase angle with respect to the frequency ratio. So so
Sir,
Sir, slides are not
excuse me, sir.
visible.
yeah.
Sir, we are unable to view the next slide, sir. I think the PPT has become static, sir.
Oh, okay.
All right. It is okay.
Are you able to
Not,
see?
yes, sir. Now it is okay, sir.
Okay,
Ah,
okay,
okay, sir.
okay. So are you able to see it now? Like the, if I put it in slideshow mode, or
Yes, sir. Yes, sir. I am. It is visible now, sir. Clearly, sir.
okay. Yeah, I think now you'll be able to see it in a slideshow mode, right?
Yes, sir.
Yeah, okay. Yeah, so basically this, so in reality there is always basically damping present in the system. So so then therefore we will get these frequency response curves for each particular value of damping ratio. So so this plot is very important. So for those, so basically this figure show, so on the left hand side we see the figure corresponding to the, the amplitude ratio versus frequency ratio for different values of damping ratio. So so you can see that as we, reduce the damping, so as we increase the damping, so the maximum amplitude uh, reduces, and then the value of the frequency ratio at which we basically get the maximum amplitude is the basically the frequency at which we observe the resonance. So but in case of a damped system, so the amplitude is like not infinite, but so there is a finite amplitude, but still the amplitude is significantly large. And as we go on increasing the damping ratio, so as the damping ratio increases beyond 1 or so, then the amplitude, so there is no resonance that is actually observed for these cases. So the uh, amplitude ratio actually just goes on decreasing with the increase in frequency ratio. So that is because the damping present in the system is so high that it actually does not give a chance for the system to uh, move to that extent that to cause resonance. So that is about the amplitude ratio part. And then similarly we have different curves for different damping ratios for the phase angle with respect to the frequency ratio. So yeah, so there is a lot of content on this slide, so just let me know whether you are like able to understand uh, what exactly is the thing that we are basically trying to show here. So any questions on this up till now?
Yes, sir, could you please this second graph, sir, phase angle phi versus frequency ratio, sir?
Yeah,
Theoretical part is okay, sir. Derivation is okay, no problem, sir.
yeah, yeah. So then what was the issue, sir?
Sir, how this curve behaves, sir, exactly, I am not getting clear, sir. This phase angle is phi is okay, sir. Frequency is okay, sir. So actually, from this curve, what conclusion we can get, sir? Like you have explained in the previous curve, sir, amplitude
Yeah.
versus frequency ratio. Can you explain in the same way the second curve also, sir?
Okay. So yeah. So for that, actually, we need to go like one step back. How do we get this curve at all? Like, so for that, so are you familiar with the concept of phasors?
No, sir.
Okay. So anyway, so maybe
Sir, you can just explain how this curve behaves. Like you have explained the first curve, sir,
yeah.
amplitude ratio versus frequency ratio. Similarly, in a very brief, sir, you can explain, sir. There is no issue, sir.
Okay. Like yeah, you basically this curve like you can mathematically it is basically this tan inverse of whatever this expression by that. So but physically what this actually means, so for that we need to actually look at the phasor representation, or in other words it's basically like a vector diagram kind of in that sense. So like basically there are different forces acting on the masses, and so each one has like a different variation. So one is like some sine theta, some other is some cos theta, so there is a phase difference between them. So how this curve is actually obtained, so based on the relative magnitudes of the different forces that are acting, so we get this particular curve as such for different frequencies and different damping ratios. So for that we actually need to visualize how this phasor representation is. So I can just quickly show you that so that it will I think help you in visualizing what is actually happening, because mathematically you can easily derive it. So basically you can use it like, so I think you know how it is derived, right? All these like how do you reach to this?
Yes, sir. Yes.
So either
Yes,
you
sir.
can use
I
it.
have already gone through that.
Yeah, so I think you can like consider like a complex number. Either you can use like a complex number kind of approach, so then that becomes easy to even visualize, and also for the algebra becomes like easier. So that's essentially what I mean by phasor. Like, so if you have a complex number, you
Okay, sir.
can
Okay,
represent
sir.
it as a vector in 2D space, and then so maybe I can just show you quickly that part. Yeah. So are you able to see my screen?
Yes, sir.
Yeah. So basically, so we have, so yeah. So basically these, like, if we draw the free body diagram for the system like over here, so, and write the differential equation of motion. So, so in, so these are the usual, if we assume x is x e to the power j omega t, so in a complex number form, so then if we differentiate that, so it becomes x dot is j omega x e to the power j omega t, and then again differentiate it twice to get x double dot, so that becomes again minus omega square times x into g to the power e to the power j omega t. So, so what this means is that multiplication by j omega, so in a complex number domain, it corresponds to a rotation by 90 degrees in counterclockwise direction. And when we again differentiate x dot once more, so then it is again multiplied by j omega, which means that it is again multiplied by, it's again rotated by 90 degrees in phase. Uh, so because complex number j, it has a, basically an argument of 90 degree. So multiplication, so by the, so you must be familiar with the rules of complex number multiplication. So when we multiply two complex numbers, so there is a rotation, so the resultant is basically rotated by some angle with respect to the earlier. So in this case, so when we differentiate, so we are basically multiplying by j omega. So then therefore x dot is 90 degrees rotated with respect to x, and again x double dot is again further rotated by 90 degrees with respect to uh, x dot, so which is basically corresponds to 180 degree out of phase with respect to x. So because Now we can also see it from here, like it is minus omega square times x into e to the power j omega t. So it is, its amplitude is, or magnitude is, omega square times that of x, and the phase angle is 180 degrees with respect to x. So now if we draw it as a vector, so let us say if x, so this angle, let us say, corresponds to omega t. So kx will be this vector, cx dot will be basically now rotated 90 degrees with respect to this. So it will be some, so minus m omega square x will be basically correspond the vector corresponding to the uh, the mass into acceleration part. So just hold on a second. So were you able to follow till this point?
Yes, sir. Clearly, sir.
Yeah. So do you agree with this point? So basically, like when we add these vectors together, so or phasors, and so basically these will be rotating. So with uh, so because omega t is changing with time, so these vectors will also be rotating, but with respect to each other, they will be changing in the way like just I have shown, like so they will be rotated with respect to each other. So now, uh, so what this phase angle actually means is that, so when we basically derive the uh, response, so we get like two parts of like the response. So one is basically the amplitude and other is phase, as I just mentioned. So when we uh, so then there is another part which is basically the force. So So I actually forgot to show the harmonic excitation itself. So let us say this. So F is equal to,
Sir, you can add now, sir. Resultant will be F0, sir.
yeah, exactly. So it will be basically F is equal to F naught e to the power j omega t. So yeah, exactly. So resultant will be F. So basically this is like resultant F0. So now the phase angle is basically the angle between these two things. So does that make sense?
Yes, sir. Actually, the sir has explained the same method using sine cos function, sir. Like you have taken the complex number j factor, but sir
Yeah.
has explained with the sine function.
Yeah, so you can do the same thing by using sine cos function also, but then it becomes like complex, like algebra becomes like slightly more. So then this is very easy to visualize, right? So it's like
Yes,
just
sir.
simple
This
vector
is
addition.
very much clear, sir.
So then these things are like, so sine and cos, they are like 90 degree. There is a phase difference of 90 degree between them, right? Then, so that's why then, because kx function will be associated if like if x is some x cos omega t something, then if we differentiate that, and it will this j omega will correspond to the sine thing, so then there will be 90 degree phase difference between them. Then if you differentiate once more, then it will become like sine will become cos, then again differentiating will become minus sine. So it's again minus 180, like 180 degree plus or minus 180 degree phase difference. And then when you add all these different sine and cos terms, so you will get finally some sine, like some sine omega t plus phi. So that phi thing is basically the phase difference. So what you get, so this is like vector addition. With that you basically know what is the phase difference between the amplitude phasor and the uh, force. So when there is some damping
Yes, sir.
present, so physically what this phase difference means that when there is certain force applied, because of the damping there is some lag created in the system, so there is some delay in the response. So 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 when the force is like oscillating sinusoidally doing something, so then system will take some time to respond. So let us say, uh, so if force is like doing something like this, so the moment the force is applied, if there was no damping present, the amplitude will also respond like that in a similar way. But because of the damping present in the system, there is some lag in responding to that. So then there will be some time gap, or in, so that is also interpreted as phase difference. Because so so when there is a lot of damping present in the system, there will be a lot of lag. So system will take more time to respond to that same force. So like, so the moment at which force reaches its maximum, displacement will not reach its maximum. It will reach after, let us say, a few seconds or few milliseconds or microseconds later, depending on the frequency of the excitation. But basically this phase difference is created because of the damping mainly. So that's the main thing. So if you had this j omega c, so if there was no damping, then this j omega c thing would be 0. Then whole this minus m omega square x vector will actually directly come onto this kx vector. So then there will be no phase difference in between the force and the uh, response, basically the displacement. So
Yes,
are
sir.
you able to visualize that?
Yes, sir. There is a small question here, sir. Sir was telling in video lecture that when omega is very small as compared to omega n,
Yeah.
Then phi will be very small, sir. How he concluded this? I couldn't understand, sir.
When omega is very small as compared to
Very
omega
very
n.
small as
Okay.
compared to natural frequency of vibration. Then phi will be very small, sir.
Okay.
Sir, how we can conclude that, sir?
Okay. So yeah, so omega is much smaller than omega n means basically that when the excitation is like the frequency of excitation is very small as compared to the
Yes, sir.
resonant frequency.
Natural. Yes, sir.
Yeah, natural frequency or resonance frequency. So then in that case, uh, basically, even though there is some damping present in the system, it will, I think, uh, in that sense, like not cause that significant of a problem in terms of. So definitely this phenomenon will still be there. Like, if you increase damping, still the phase angle. So if you like consider, let me just shift to uh, my presentation slide.
Sir, it may possible that when omega is very small, then the effect of damping will be very small, sir. We can say in this way also, sir.
No, I don't think
That is
it's.
why.
No, I don't think it is. It like I think he meant that. I think he meant something else. I don't know. But yeah, just let me. Yeah. So yeah, what I mean to say is that uh, so when the frequency ratio, or basically when the omega is much smaller than omega n, then you will be basically somewhere in this operating in this some zone. So you are able to see my pointer, laser pointer.
No, sir.
You are not able to see where I'm pointing to in the figure.
No, sir. Slides are
Yes,
not
sir.
visible, sir.
Not visible. Uh,
No, sir.
just let me. Now are you able to see?
Yes, sir. Visible now, sir.
Yeah. So okay. So basically, I think what he means to say is that,
Yes, sir.
so when your omega is much smaller than omega n, so you are basically operating somewhere in this zone where my pointer is. Now you can observe that uh, when the damping ratio is increasing, you will see that. So if you like uh, draw a vertical line over here, so for the same frequency ratio, as you go on increasing the damping ratio, the phase angle will definitely increase. So damping will definitely cause an increase in the phase angle, uh, because because of the lag created, because just what I mentioned like a few minutes back, like damping creates a lag, so that's why it creates a phase difference. So that will definitely be there. But I think what happens is that as you approach the resonant frequency, then irrespective of what your damping is, your phase angle still remains like it. Damping has no effect. So at the when you are at the resonant frequency, you can see that all the curves are intersecting at the same point, right? Right. So here you can see that all your curves are passing through the same point. So the phase angle is 90 degrees regardless of the value of damping ratio. So are you able to see what?
Sir, actually, when omega by omega is very small, sir. Obviously, phi will be small, but sir, there will be effect of zeta also, sir. If you see the curve here, sir, when the frequency ratio is quite small, sir.
Mm-hmm.
Okay, still we are getting a value of phi equal to 60 degree or 35 degree, sir. So
Yeah,
actually,
yeah,
the value of phi depends upon zeta also, sir. Not only on frequency ratio, sir.
yeah, exactly. Yeah, exactly.
Yes,
So
sir.
now what happens, like, so if you just now if you turn your attention to this expression, phi is equal to tan inverse of this 2 zeta r upon 1 minus r square. Now when r
Yes, sir.
approaches the value of 1, then what will happen, regardless of what the value
No,
of
sir.
zeta is, it will
When the
become.
when the sir, when the value of r approaches to zero, sir, because omega is very smaller,
No, no, I am
so we
talking
will
about.
take omega by omega into 10 tending towards zero, sir.
Yeah, 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 for very small values of frequency ratio, it will become nearly tan inverse of
Zero,
2
sir.
zeta r. The
Yes, sir.
ha,
But this
so
is true only when zeta is equal to zero, sir.
no, no, no. I am saying that when zeta is equal to 0, then there will be no phase difference at all.
Yes, sir. Phi tending to
Now,
zero, sir. In that case
yeah,
only.
yeah, exactly. Now,
But
but
sir,
when.
but but in actual practice, we encountered a significant value of zeta, sir. Maybe zero point 0.3 or zero point 0.4, sir, or even zero
Right,
point 0.2, sir.
yeah,
In
yeah.
that case, phi will be significant. Phi will have a significant value, sir. That is my objection, sir.
Phi will have a significant value because of the damping. So if you increase damping, then you will obviously observe significant value of the phase angle. So you can see here, like, even when the zeta value is like even 0.25 or zero point 0.5 or something like that,
Yes,
so
sir.
still the
Yes,
phase
sir.
angle is like 20-30 degrees. That
Yes,
is,
sir.
yeah, so that is because of the nature of the damping itself, like. So this you cannot like make just a generalized statement, like that, for
Okay, sir. Okay.
like that.
When zeta is small, then we can say phi will be approximated to zero, sir.
Yeah, when zeta is very very small
Yes, sir.
and for very very small
Of
values of
frequency ratio.
frequency ratio, then you
Yes,
can
sir.
say
Only
that.
that case.
So like that we can say, yeah, so like that.
Yes, sir.
Okay. Yeah, so I think Prashant has something to say. For all values of zeta,
Sir,
then
Prashant sir is saying that irrespective of zeta, phi will be zero if we reduce the value of r, sir.
yeah, yeah, right,
Sir, that we can interpret it from the graph itself. But
yes.
if we use the formula of tan inverse, sir,
Mm-hmm.
then we will not getting phi equal to approximate equal to zero, sir. That is my objection, sir.
Can you just repeat once more what you said?
Sir, say zeta is equal to zero point 0.5. If we assume zeta to be zero point 0.5,
Mm-hmm.
okay, sir. In
Right.
that case, phi will have a significant value, sir.
Yes, it will depend on, now it will, so if you consider like a particular value of zeta, say zero point 0.5 as you said, now it will depend on what is the frequency ratio R. So if it is, again it is, if it is very small, R, if R itself is very small, then the phase difference can be very small.
Sir,
But
it may be 20 or 25 if you read the graph carefully, sir.
for what value of phi? So for what value of frequency ratio?
Sir, anything between 0 and zero point 0.5, sir.
Yeah, it can be, yeah, so it can be like more than 30 degrees also.
Yes, sir. That I want to say, sir.
Yeah, so it can be like, it can be, it's mainly because of the damping and the frequency ratio combined together.
Okay, sir.
So so what happens is that, so when you
Sir, when zeta is small and frequency ratio is also small,
yeah,
then phi tend to zero, sir. I think that is the
yeah,
correct conclusion.
yeah, exactly, that is true,
Yes,
definitely. When you, your frequency ratio is also small and zeta is also needs to be small. If if you increase value of zeta, then again you will have significant value of phase angle.
yes, sir. Yes, sir. Yes, sir.
So as I told you, when you go on increasing the damping, the resistance to motion, it goes on increasing significantly, and as you like increase the damping values beyond 1, then the damping is such that the system cannot move at all. So the force goes on doing something like
Yes,
the
sir.
force, there is a lot of oscillation, but the system does not get enough time to respond to that excitation because of the very high damping present. So then it creates a significant lag. Another thing is
Yes, sir.
like, another thing is, if you, why phase angle is also increasing with frequency. So when you uh, so go on increasing the frequency of the excitation, so let us say even like beyond the resonant frequency, then the excitation is so fast that the system does not get enough time to, so in any mechanical system, it will take some time for it to respond, right? So if your excitation is like, kilohertz some or megahertz or something, but your natural frequency, let us say, is some hertz, few hertz and something, so in that case your system will not be able to react so fast to any excitation. So that's why you will see significant values of phase angle for very high frequency ratios. So it will cross 90 degrees and go on increasing till 180 degrees. So physically there are two things, like if damping is present, that will cause lag. Another thing is because of the frequency of the excitation itself. So if frequency is very high, then again that will cause a lag in terms of, so if you see, like if you are able to visualize that, uh, so are you able to visualize what I'm trying to say?
Yes, sir.
Yeah, so if it's like, if you kind of, if you visualize the spring mass damper system, and if I connect some oscillator to that block of mass, and if you vibrate it, let us say at like, you know something like some kilohertz or something, so then the oscillation of the block becomes so fast that it's basically not able to react that quickly to, so let us say the force is reaches its maxima, but the displacement will reach its maxima maybe probably after completing half cycle of the force, or even more than half cycle of the force. So it will reach its maxima somewhere after that, like let us say completing half the cycle of the force oscillation. So it can happen like that also. So there are like two things playing a role. So both the damping as well as the excitation frequency.
Okay, thank you, sir.
Yeah. Yeah. So any other questions or comments? Okay, sure. So then I think we can move to the problems. If you don't have any further questions, then we can actually go over some sample problems. If you, so I think there are some other participants also who have joined us. So Mr. Uh, Dalan, and so
Yes, sir.
yeah, hi. So did I pronounce your name correctly? Dalan, right?
Yes, sir.
Yeah.
Dalan.
Yeah. So is this the first time that you joined this session?
No, sir. I joined the previous past session you have taken that.
Okay. 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 Sure. So yeah, welcome. And yeah, so basically we were discussing about the some of the course content and some of the doubts related to that. So if you have any questions from your side, like do let me know. So do you have any questions?
No, sir.
Okay. And what about the others? Like anyone else has any question?
Sir, I have one a query regarding energy supply to the system for vibration, sir.
Mm-hmm. Okay.
Sir has solved a question numerical problem in the video lecture
Okay.
in which it was asked to calculate the power required to vibrate a system which has three components: a spring, mass, as well as damper, sir.
Okay.
So my simple question is that in this question where we are being asked to calculate the power required to vibrate the system.
Mm-hmm.
Okay, sir, should we calculate the energy input or energy dissipated, sir? Because sir has calculated energy dissipated by the system, sir.
No, can you just repeat your question like once more?
Sir, question was that calculate the power required to vibrate a system. Okay,
Oh,
now system consists of these three standard components, sir:
right.
mass, spring, as well as a damper, sir. So my query is that in this question, should we go for calculating the value of energy required, and that means energy input to the system, or should we calculate the energy dissipated by the system? Because sir has calculated energy dissipated by the system, but the question says that you have to calculate the power required to vibrate the system, sir. So I got confused, sir, because there are two term: energy input and energy dissipated by a system per cycle, sir.
Okay. So first of all, is it a case of forced vibrations or free vibrations?
Sir, it was a case of force vibration, sir.
Yeah. So if it is a case of forced vibration, so then there will be like the so one part is the energy dissipation, that is because of damping. So you can calculate the energy dissipated by basically integrating the work
Yes, sir.
done
There
by
are there are standard formulas available, sir, because sir
yeah.
has derived the formula. My simple query is that in this question, where question say you have to calculate the power required to vibrate a system.
Yeah.
So should we calculate energy input to the system or energy dissipated by the system? Because there are two different formulas for two different cases, sir.
Yeah, so here if you want to calculate like if that what is the power required to drive that thing, so then
Yes,
it's
sir.
basically the energy input from the excitation, which is
Yes,
the
sir.
energy supplied or energy input. So because that is the energy coming as an input to the system, right? Because of the
Bec-
excitation itself.
Yes, sir, sir. So
And then
my stance is that we should go for energy input system, but sir in video lecture has calculated the energy dissipated by the system, sir. So I
uh,
was little bit confused, sir. Sir, would you clarify on that point, sir?
okay. So if you so let me check.
Sir, this question is available in the slides also, sir.
Lecture
Week three
slides,
slides,
okay.
sir. Week three slides, sir.
Okay. So so is this the question that you were talking about? I am sharing my screen right now. Okay. Determine the power required to vibrate a spring mass dashboard system.
Yes, sir.
Okay. See, so there is certain energy input, so given to the system, which is basically, uh, so here actually there is only the frequency of excitation that is given. The steady state amplitude is given 1.5 centimeter. So there is a damping factor given and damped natural frequency is also given. Now they have not like given like this is the amplitude of the force of the excitation. So yeah,
Sir, it will be a force vibration, obviously, because
it
we
is a
are
force
supplying,
vibration. Yeah,
yes, sir, because we are supplying energy in the form of force only, sir.
yeah, exactly. So when there is a certain forcing being provided, some part of it is basically spent in basically stretching the spring, right? So some potential energy will, so when you stretch the spring or compress the spring, there is some energy that is being stored in the spring. So some part of the power supplied will be basically spent in, which will be going to the as a potential energy of the spring, and other part will go as kinetic energy of the mass, right? And the third part is basically some part of the energy is dissipated because of the damping.
Yes, sir.
So the sum of all these three things will be basically the total energy supplied to the system. And
So, sir,
so
yes,
that,
sir.
yeah,
So power required means we have to calculate it power. That means energy input the system or energy dissipated by the system in the form of damping, sir. That is my query, sir.
yeah, I think it is mainly the power, total power supplied or energy supplied per cycle.
Sir,
So
yes, sir.
total energy supplied in one cycle divided by the time period will be the
Yes, sir.
total average power required, right?
Because sir, in video lecture, sir has only calculated the energy dissipated by the system.
Yeah, that is just one part of where the energy is going. Some part of the energy will go into dissipation. Then other
Okay,
part
sir.
will be spring, like so there is a spring, so then it will have some potential energy. So that will also keep on changing, and kinetic energy of the mass will also keep on changing. So so basically it will so this power required will depend on, as I told you, kinetic energy of the mass, potential energy of the spring, and how much power is being dissipated. Basically, it's the sum of all these things together.
Okay, sir. That means we have to calculate energy input the system, total energy input, sir.
Yeah.
Okay, sir.
So if it was specifically asked that you need to calculate energy dissipated only. So see here in this
Sir,
slide,
because the confusion arises because sir has terminated the question just by calculating the energy dissipated.
then I think you must
So,
have somewhere said that you also need to calculate the other parts of the
okay,
energy.
okay, sir.
Yeah, I think you must have said somewhere. I think. Yeah, I do not exactly recall the particular thing, but I think so. In this slide also he has mentioned energy input and dissipation. So there means like, so he has separately considered dissipation, and then energy input will be basically the work done by this force per cycle, like basically.
Yes, sir.
Yeah,
Because both have different values for any system, sir.
yeah,
So if we only calculate the energy dissipated, I think the question will be incomplete, sir.
yes, yes, obviously,
Yes.
yes, yes, right, sure. Yeah, thanks for bringing that up. So that's an important, again, an important concept.
Okay. Thank you, sir.
Any other questions? Yeah, so I think you are also, Prashant has also, I think, summarized the same thing. Like, yeah. Okay, so then shall we move to the problems part?
Yes, sir.
Okay, then we'll go through some sample problems now. So yeah, so I have like picked up some sample problems which are related to the concepts for this week. So if you have any specific problems of your own which you want to discuss, you can also bring them up at any point of time. Uh, so yeah, so we can go through this sample problems which I have uh, pulled out. So the first one is basically a damped system when excited by a harmonic force has a magnification of 5 at the resonance frequency. So the damping ratio will be what? So so that's the question. So for that we have to refer to the expression for the magnification factor. So which is so as a function of the so we'll write directly the expression for the magnification factor as a function of the frequency ratio and the damping ratio. So right now I'm assuming that you are already familiar with this terminology. If you are not, so just let me know. So do all of you understand like what this expression that I wrote? Yeah. So it's basically given that this magnification factor is 5. Sorry. So then so we have to solve for the uh, damping ratio zeta. So how do you think we can solve this problem? Okay, for r equal to 1. So yeah, so we can put r equal to 1. So that is one way. Yeah. So then this term becomes 0. So then it will be basically 1 by 2 zeta r is 5. So r is already 1. So it will be 1 by 2 zeta. So when zeta becomes zero point 0.1, right? Make sense?
Sir, I have a query in this formula, sir.
Yeah.
Sometimes, sir, I have seen in some of the numericals that then omega is more than omega n, sir. So can we
Yes.
apply the same formula when omega is greater than omega n, sir? Is it possible feasibly, sir?
What do you mean by omega is greater than omega n?
Sir, suppose we have a excitation force on a system whose frequency is more than natural frequency, sir.
Mm-hmm. Yeah.
So in that case, omega will be larger than omega n, sir.
Yes.
But since we are subtracting it from 1, sir,
Mm-hmm.
so will it affect my calculation, sir, if omega by omega n
Mm-hmm.
is larger than 1, sir?
1. Yeah. Yeah, yeah, no problem with this formula because it is already
Okay, sir.
squared. It is already squared,
Okay,
right?
okay, sir. Okay, sir.
So 1 minus r square, if it is negative, it is still squared, right? So then that will not be a problem.
Okay, sir. Okay, sir.
So value of this expression in the denominator will always be positive. So there will be
Okay,
no
sir.
numerical issue with respect to that. So yeah, now if we actually define that, so for, so this is when we equate r is equal to 1, it actually means that we are, so omega r equal to 1 means omega is equal to omega n, but omega is equal to omega d. So if omega d is basically the damped natural frequency, so which is omega n into root of 1 minus zeta square, right? So now one can also define that resonance is, so when this omega is equal to omega d. So for that, so now we generally consider like resonance with respect to the undamped natural frequency. So that r equal to 1 is the resonance. But if you look at the graph carefully for the, for the frequency response curve, just check whether it has its maxima for the amplitude or magnification factor. Does the maxima occur exactly at r equal to 1 for each case of damping ratio, or does it change? So let's just carefully look at that. So one, this is like when we say r equal to 1, we are saying that our frequency of excitation is same as the undamped natural frequency. But in reality, the system is always damped, right? So then, so do you think we should call omega is equal to omega d as the actual resonance? What do you think?
Yes, sir. Other than resonance, sir.
Yeah. So it should be the damped natural frequency, right? So let's just quickly look at again. Let's just quickly look at. So let's just quickly look at the chart that which we just discussed for the amplitude or magnification factor. Yeah. So if we look at the chart of the amplitude ratio or magnification factor here, we can see that, for, let us say, let's look at the curve for zeta is equal to 0.3. So do you see, so here this dashed vertical line is the line corresponding to frequency ratio is equal to 1, which is r equal to, so which means omega equal to omega n. But is the maxima occurring at r equal to 1?
No, sir. A
No,
little
right?
bit earlier, sir.
Little bit earlier, right? So it's actually occurring at the damped natural frequency. So if we define that the resonance as the frequency for which the amplitude ratio is maximum, then it is this maxima, it occurs at actually earlier, slightly earlier than the resonant frequency. So that is actually the maxima corresponding to the damped natural frequency. So we can actually check that, we can actually derive it for that particular uh, every damping ratio and check that. So to yeah, so omega by omega d will be maximum in that case. Omega by omega d equal to 1 will be the point of maxima for that thing. So now if somewhere if we define that omega by omega n is equal to 1 is the resonance, then okay, then we can say r equal to 1 in that case is the resonance, and then calculate the magnification factor with respect to that. But if we define it with respect to the damped natural frequency, we will have to use it in that sense, like otherwise. So there is a small difference between them. It may not be very significant, but like if we are actually looking at a exact numerical calculation of that, so then it will slightly change our answer that we got, like whatever value of zeta that we got. So we just simply substituted r equal to 1 here. But if we have to find out the frequency at which m is maximum, so then we have to differentiate del m by del r. So basically derivative of the magnification factor with respect to the frequency ratio to find out the value of r for which this magnification factor is maximum. Or now, because the expression in the denominator, so when m is maximum, the denominator should be minimum, and since the expression inside the square root, it's a monotonically increasing function, so we can just say so what I mean to say is so if we differentiate this expression with respect to r, so we will get the value of, so by the principle of maxima minima, it will be basically the point at which this derivative is 0. So then it will, so so it either means r is equal to 0 or So this is the value of R for which the basically the maxima of that magnification factor will occur. So it's, you can see that it is root of 1 minus 2 zeta square, which means that it is slightly less than 1, right? So the maxima of the magnification factor which will occur slightly before r equal to 1, right? Make sense? Okay. So like that's an important thing to note generally. Yeah. So here, so we have been given a simple spring mass damper system, the value of spring constant mass and the damping have been given. So we have to find the steady state response and the total response of the system under the harmonic force. So now in this question, what is, how do we understand what is steady state response and total response? So what is basically steady state response?
Sir, X0.
So what do you mean by x0?
Sir, it is zero point 0.1 meter, sir.
No, that is not the steady state response. So that's the initial condition. So x naught is basically the initial displacement and v naught is the initial velocity of the mass. So uh, with respect to the parts of the
Steady
response,
state means steady state means when only 400 Newton force is acting. There is no transit part associated with it. F0.
right?
Deflection under F0.
Correct, right. So yeah, x. So basically, after now, because there is some damping present in the system, so initially the system will respond as per its own natural frequency. So there will be a transient part of the response, and then after sufficiently large number of cycles of the forcing, the because of the damping part, the free vibration, or basically the response of of the system because of its own natural frequency, that will slowly die out because of the damping, and then the response, in the response there will be mainly only the oscillations present because of the harmonic force at the frequency of the same frequency of the harmonic force. So that will be the, so the system will continue to oscillate at the frequency of the harmonic excitation till the harmonic excitation is still like acting. Once that stops acting, then again the system will respond as per its natural frequency. So it's like, if you switch on the harmonic force excitation, initially the system will take some time to pick up and stabilize at the steady state to steady state, and then once we switch off the harmonic force again, the system will respond as per its natural frequency, and then the amplitude will slowly die out. So here, in terms of the differential equation, so if we write the differential equation for this forced vibration case.
Sir, excuse me, sir.
Hmm?
Do you mean that the harmonic force will be removed after a particular time, sir?
No, I mean, it's not necessary that it will be removed, but I'm just saying, like, if we uh, happen to remove the excitation part, then again there will be no energy input further to the system, right? So then it will respond as per its own natural frequency, and it will, the oscillations will slowly die out, right? Yeah. So when we write this differential equation, so when we solve such a differential equation, so what are the two parts of the solution that we derive?
Sir, CF and PI.
Yeah, so what is CF and PI?
Sir, in complementary part, we make the equation equal to 0, sir.
Right, exactly. So that is basically exactly same as the free vibrations, right? Because right hand side is 0, that means the system responds to the as per the natural frequency of the system, and then the right hand side is something. So then, so the other part will be basically the particular solution. So that particular solution is same as the steady state response. So the response will have two parts. One is basically the complementary function and the particular integral. So particular integral is same as the steady state response, and the uh, complementary function is the transient response, right? So now if we assume again the same way, like x is equal to some x naught e to the power j omega t, and substitute, so we will get, so in terms of, like, if we again go by the phasor or complex number whatever approach, so then we can find a steady state response in this way. So we can basically get that x naught is f naught, so or basically magnitude will be So this will be our steady state amplitude, right? And what will be the phase? What will be the phase angle? So it will be,
C omega divided by
yeah, so it will be basically tan phi is equal to,
K minus M omega square.
right? So this will be our phase angle of the steady state response. So it will be x naught cos omega t plus phi. So where x naught is given by this thing. So steady state response will be x naught cos omega t plus this phi. So where phi we can get from this tan phi is equal to this thing, and x naught we got it from here. So this expression f naught by root of whatever expression. Now comes the other part of the which is the complementary function. So for that we need to check whether the system is in what kind of damping it is. So you have like three kinds of damping, right? So one is under damped, over damped, critically damped, etc. So we need to check whether the system is like what kind of damping is present in the system, right? So how do we check that? So we need to first find out what is omega n. So omega n is root of k by m. So which is 4000 by 10, or so which will be basically root of 400 or 20. So it will be 20. Then what is the value of critical damping? So it is 2 root km, right? So it's
Sir,
basically, huh?
for
Sorry.
400. It comes out to be 400, sir.
Yeah, okay. So it's 400. So, and the actual damping value is 40. So zeta will be C by critical damping.
Yes.
So which is
Point 1.
0.1. So it is basically under damped. So then we can assume a certain kind of response, right? So which is already known to us. So it's already derived. So we know that, the complementary function part will be basically some, right? Is that correct?
Sir, is it for complementary or particular, sir?
This is complementary function because this is the solution form for, because it's an underdamped system. So it is solution to that mx double dot plus cx dot plus kx is equal to 0, right?
Yes, sir.
So it's the complementary function, solution to the homogeneous differential equation.
Yes, sir.
So
Sir,
then,
my query is that in the previous slide you have write x is equal to x0
mm-hmm.
cos omega t plus 5, sir. This
Ha
is
ha ha.
this was the solution for pi part, sir.
Don't confuse that x naught with the initial condition thing. It's just like,
Okay, okay, sir.
yeah. So it's basically the steady state amplitude value. Yeah. Let me just, instead of x naught, let me just say,
No, sir, my query is that should we write omega t minus phi, sir, because system will respond by a phase lag of phi, sir. Why we are saying plus phi here, sir?
no, phi can come out to be negative also.
Okay,
So,
sir. It is
so
generalized, sir, you say.
yeah. So it like, so if our omega, this omega c by k minus m omega square, so k minus m omega square can be negative. So if that is negative,
Okay,
phi
sir.
can be negative also. So like that, it's possible. Not necessary that, so that it will always be positive. Yeah, and now this is our complementary function. So our total response, so we will have to apply our initial conditions to the sum of both the responses. Basically, so our total response x will be, so this is our particular solution, right? So let's write as, let me write it as xp. And then after adding this, then we apply our initial conditions that x of 0 is equal to x naught, which is 0.1, and x dot 0 is 0. So for that, then we can just, differentiate this these two expressions, and then like derive what is the, so the unknown constants a and b can be found out using the initial conditions, because now we have two initial conditions. We can find out the value of the two unknown constants a and b from that. So that's how we can solve this problem. So do you want me to actually solve, like, do the differentiation and everything, or like you can do it on your own?
Sir, we
See,
require time to solve the question, sir.
yeah, so you need some time to solve this question. But yeah, so will this kind of question be asked in the examination? Because this is very lengthy. Yes, I understand it is lengthy, but I think, I believe that, you will be mostly be given multiple choice kind of questions for these NPTEL kind of things. But to understand like the basic things, these kind of questions will help you, getting the your basics, like, so yeah. So so if you, like, look at the kind of questions that you encounter in assignments, like those are like very very specific and direct questions. Like they will have, like, one answer, like, so it will be, you will have to do a small calculation and something like that, and then you will just get the answer. So yeah. But yeah, so if you go through the entire derivation and all these things, then you will actually get to know what is actually happening. So it's like good to understand, to solve like this, solving these kind of questions will help you just understand what is actually happening. Okay, then yeah, maybe I'll. So I think you can just try this, like deriving these things on your own, like like if you add, so we have already derived the expressions for the complementary function and particular integral, like both. So then if you add them, so we have to apply initial conditions to the sum of both these things. So the total response, not just complementary function or particular integral. It's a total response and initial conditions applied to that. So so you can do the differentiation and I think on your own. So you can, like just you have to uh, like take the derivative with respect to time, and then you will get the answer, I think. So yeah, I think so. Let's move to another example. So an industrial machine which is weighing 445 kg is supported on a spring with static deflection of 0.5. So there is a rotating imbalance and the speed of rotation is given. So we are again asked the same, like the dynamic amplitude of the machine. So dynamic amplitude means basically same as the steady state response to the excitation. So you know the mass and the static deflection is given. So we can find out mass into g as the static deflection. So it's basically so from that you will get the value of k. So the rotating imbalance is given, which means that the mass into the eccentricity into omega square, so will be the amplitude of the force, so which is 25 kg centimeters, and omega, it's basically 1200 rpm. So in terms of radians per second, so it's basically like this. So this will be the amplitude of the force. So then you need to basically do the same thing, that now here it is, there is no explicit mention of damping. So then we can just assume that there is no damping present. So it's just one spring mass system with some forcing harmonic excitation because of the mass rotating imbalance. So then we can find out the steady state response by, so basically it will be, so if we solve the differential equation or derive the differential equation, and so this will how it will look like. So So if we again go by that same approach, that then we will get, sorry, uh, yeah, yeah. So our steady state amplitude will be, so this will be our steady state amplitude. So we basically know what is the value of K, we know what is the value of capital M, we know what is this small m into E. So everything omega is also known to us. So from that we can just substitute the values and find out what is the steady state response of the system. So is that clear?
Yes, sir.
Okay. So I think
Sir,
we can,
should,
yeah, yeah,
should we go for say another part also, sir?
yeah. Another part in the sense.
Like we have done for steady state response, sir. Should we go
So
for transient part also, sir?
no, here, yeah, you can go for, but like there is no initial condition given, so you can assume some initial condition and also derive like what is the like the complementary function part also. So like
Yes, sir.
natural
Because
frequency,
constant cannot be found out without initial conditions, sir.
so you need to have some initial condition. So either you can assume something or you can just like uh, take some like zero initial condition or something.
Sir, these equation which we have formulated for rotating unbalancer,
Mm-hmm.
do they belong to longitudinal vibration or transverse vibration, sir?
It actually depends on the problem like you are looking at. So whether it is longitudinal or lateral or whatever, like it depends on uh, it's mostly, like
Most,
the
I think, sir,
it's mostly
they
okay.
are longitudinal, sir.
No, what like in what context are you looking at? Like I did not get your question actually. Like
Sir, like suppose we have a rotating machine, sir, and there
mm-hmm,
is some unbalanced mass, sir.
mm-hmm,
So as we have done in case of in this problem, sir, we have calculated the response, sir. That response is only in x direction, sir. But the y component of the unbalanced force will cause the another type of vibration also, say in the transfer direction. So if we assume this is a longitudinal
ah,
vibration, then its y component will create the transverse vibration also, sir.
okay. So that
So
way, yes, yes. So it's like, yeah. So if you consider the direction in this F vector is acting as longitudinal, yes, so it is longitudinal. But if like if we restrict the motion of the machine in a particular direction
yes,
only,
sir. Yes, sir. By
then
by
there is
bearings.
So using bearings or whatever. So if I did not draw it explicitly here, but let us say if we say that, there are
So
some.
generally, sir, my question is that generally these type equations are considered for longitudinal vibrations, sir. If the other direction is restricted, sir.
So if the other direction is constrained or restricted, so then you will only see vibrations in one direction. So in
Okay, sir.
other directions, so if this was not there, this whatever I have drawn, these rollers or whatever bearings, then it will also tend to oscillate in the other direction also because rotating unbalance will have like both x and y components. So yeah, you're right. So it will be in both directions. Okay. So I had one more interesting example, so which we can, I think, quickly discuss for now, and then maybe we can discuss the solution later on. But yeah, so I think since you had like earlier you had asked for some practical discussion on some practical problems.
Yes, sir.
So yeah, so this is one kind of a practical problem. So so we like basically have like car going over a speed breaker. So that is again a problem in vibrations. So if you go through a road of where you have frequently have to go over speed breakers, so then uh, depending on the speed of the car, you will feel the the impact of the speed breaker. So then like this problem talks about that, like, so if we consider a car going over a road whose elevation it's actually varying sinusoidally, let us say, and the road is not, I mean, so this is not exactly the real way in which roads are actually, but let us say if we approximate the terrain in such a way that it follows like a gently increasing and decreasing sine wave. So so generally the height of the speed breaker, let us say it is suppose 10 centimeters or something like that, and the distance between consecutive speed breakers, let us say, or high or maxima of the uh, road elevation is, let us say, it is given at, let us say, 35 meters, which is some reasonable value, let us say, and the natural frequency of the automobile, let us say, is 2 hertz. The damping ratio of the shock absorbers is also given. Now if we want to determine, so if the uh, car is going at a speed of, let us say, some 60 kilometers per hour or something, let us say we want to determine the amplitude of the vibration of the automobile. So so the suspension has some, the stiffness, and then uh, so then so depending on the stiffness of the suspension and the natural frequency of the automobile and how much damping is present, the passengers will feel the bump as per that. So now to actually estimate that, like, how like, so if we now are looking at a simplified kind of a way or to find out what how much up and down motion of the car like happens. So for that we can actually look at simplified models of the car. So now it actually depends on, like, so since you brought up this uh, part, like, practical problems. So now how can we model this a car going over a road? So there are different approaches, and depending on how much information that we have available with us, and what is the level of accuracy of the results or very level of detail at which we are looking at. Depending on that, we will select what kind of model we require, right? So here, let us say we have like just basic information of the how much is the weight of the car, how much is the stiffness of the suspension generally, and what is the typical mass of the wheels and everything, like those kind of like if we have like very basic information, so then we can go for a single degree of freedom model where we just model it as a lumped lumped mass, like the entire car body as a lumped mass, and uh, the suspension, the stiffness of the suspension as another spring, as a spring, let us say. So then that becomes and the damping value of the, let us say, shock absorbers or whatever that is known, so that will be the damper. So all the four wheels lumped together and the car body together, like that was like, let us say, one mass. And sorry, I'm sorry. Yeah. So if we consider like the entire mass of the car and the four wheels, etc., is lumped into one single mass, and the stiffness of the suspension is modeled as one spring, one single spring of all the like suspension of all the four wheels together, and then the damper as one common one. So then we can represent the whole car going over the road as a single degree of freedom system. But now if we are interested in like how much front wheels are going up, and then again when the car crosses the bump, like the front wheel crosses the bump, and then again how much are the rear wheels again going to go up, like that. So if you are looking at like very detailed that kind of model, so then we'll have to model like front wheels and rear wheels separately. And if you are also looking at when which, like let us say, front left wheel and the separate like individual motions of all the four wheels separately, then we'll have to again go for another more detailed model where we have to model all the four wheels as separate masses with separate spring and damper values for each wheels and their suspension. So yeah, so like depending on how much information that we have and what is the kind of analysis that we are looking at, so we can decide like different models that we can use. So yeah, so I think it's almost time up for today's session. So I think we can continue discussion on this later. So so I hope this discussion was some interest, right? Was this of some interest? Yeah. So yeah, so I think we can continue discussion on this. So I'll also be sending you these slides, so you can also try solving these things on your own. So there is one more problem which I had along with this, so you can try it out. And yeah, so just let me know whether you are able to solve this, and we can discuss the solution next time. Uh, so yeah, yeah. So I'll share the answers of the questions. Yeah. Okay. Fine. Okay.
Sir, which book you are following for this part, sir? Like excitation to support and energy input, sir.
I've mainly studied vibrations from the book by S.S. Rao, and
Okay, sir.
so there are like two, three books actually on vibrations. So I had actually a list. Let me just check. So
Sir, actually, in the week three's assignment, there is no question on excitation to support and energy input and dissipation, sir.
Excitation. Sorry, can you come again, please? What were you saying?
Sir, these topics has not been covered in the assignment, sir. They are part of the weekly video, sir.
Mm-hmm.
But there is no question on excitation to support or the energy input or energy dissipation. We have just discussed, sir.
Oh, okay, okay. Okay. So, uh, so you can actually refer to SS Rao, like that book. So that has a lot
Okay,
of
sir.
problems on vibrations and like, yeah, I'll just share one slide in which I have like the list of other books on
Sir, we have
vibration.
list with us, sir.
You already have? Okay.
Sir,
So
the
I don't know. I
yes,
don't
sir.
know. Like,
Name of the books are given in the course outline also, sir. But this particular topic, sir, is not available in every book, sir.
I see. I think it must be there in SS Rao, definitely.
We'll check, sir.
And
We'll check, sir.
yeah, yeah. I think it must be there in this and this third book, Theory of Vibrations with Applications. So Thompson and Dale. So that is also a good book. So where you will find
Okay,
some
okay. Okay, sir.
related to
Actually,
rotating unbalance and
yes,
all
sir.
those things. Like you will have some good amount of problems on that.
Okay, okay. Thank you, sir.
Yeah. Okay then. So I think then we can conclude today's session here. And yeah, so I'll share the recording and slides, everything with you. So let me know if you have any questions. Yeah, and also I'll post in on the discussion forum as well. So whatever your questions were, like, thanks. So thanks all for joining. Uh, so I think we can end our session for today here. Thank you. Thanks all for joining.